Good morning, here we are once again. It's the physics video lecture, psci 168, video lecture 14. Okay, had some great material last time, namely the meteor collision. I hope people get some, meteor crater, I hope people get some good images of all of those topics. We learned about kinetic energy and work, and that's what I'm going to continue on with. And actually we'll get pretty far today. So work and start numbering things again, kinetic energy. And what we learned discussing the meteor crater and other things as well is that you can have kinetic energy whose expression is a half mv squared, and that can turn into some work. In other words, that can do some work. We can dig a gigantic hole in the ground, for instance. So if you have the kinetic energy of an incoming meteor, then, and if it's large enough, you can dig a pretty big hole in the ground. So kinetic energy can end up doing work. And we're going to pursue that. And actually we can draw the arrow the other way. You do some work first, and then you can get some kinetic energy out of it. So that's what we want to discuss in terms of the pendulum. So this is a pendulum sketch that we want to draw a large one. Actually, what we'd like to do is hang the bowling ball from a hook in the ceiling here, and we have a giant pendulum. We can do all kinds of stuff, but that's not happening this semester. Let's just draw the picture. So think of a large pendulum, any pendulum, and so it's got mass m and length L, and this is a fixed point here. And now let's draw a semicircular arc. Okay, so we go over here and here. And so this pendulum is free to swing any way, say all the way up to the level there. Now what we're also going to do is imagine we have, so I've drawn a horizontal line right through the bottom, and imagine this is the y-axis, and this is the 0. So we can measure vertical height over here, and we have a certain pendulum that can swing back and forth. Okay, we know about lifting things. So suppose we lift the pendulum. I'm going to choose this position right here. I don't want to get too wild. We call this position A. So we lift the pendulum from the bottom up to position A, and there we have a y sub A. And we let go now. Okay, let go of the pendulum. What's it going to do? It's going to swing back and forth, and eventually, if you wait long enough, it'll come to a stop. And why does it come to a stop? Because there's friction. Okay? So the ideal pendulum would actually never come to a stop. And we're going to talk about the ideal pendulum, and then the real one again. Let's draw a dotted horizontal line over to here. We're going to call this point C, and I guess we'll put B down here at the bottom. Okay, so we release the pendulum from rest, release from rest at point A, and then it'll swing back and forth. Now, up at point A, we have work sub A is equal to mg y sub A, because that's how much work it took to lift the pendulum. Didn't matter how we lifted it once we got there, that's how much work it was. Down at the bottom, W sub B is equal to 0, comma, kinetic energy, KE is equal to 1/2 mv squared. And it's actually exactly equal to W sub A. So the work that we did up here was converted to kinetic energy, and then it's going to swing back up to C here, and it'll be work again. So up at C, W sub C, or we can also call it potential energy, W sub C is equal to mgy sub C, which is equal to mgy sub A. So in the ideal case, so let's make sure we write here, it's the ideal case, comma, no friction. In the ideal case, this thing just swings back and forth. You have work or potential energy, swings down, turns into kinetic energy, goes back up into work, potential energy, and any place in between. For example, we could have a spot in between here. It will be moving and have some work. It'll be a combination of the two. We call this conservation of energy. This phenomenon that if you do a certain amount of work, you have potential energy. In the ideal case, it always stays the same. So it's distributed potential energy. In fact, let's go ahead and label this in one more way. Remember, work is the energy is the capacity to do work. So here we can say we have potential energy. Here we can say we have kinetic energy plus potential energy because it's just, moving. Down here, it's all kinetic energy, and up here, it's all potential energy. So what we have here is kinetic energy plus potential energy is constant. Individually they change. The sum of the two are constant, and that's what we call conservation of energy. So conservation of energy, one of the most important laws of nature, and this is just the really basic manifestation of it. Okay, and this constant business is so important. Remember I said if there's friction, it would actually decay, and after so and so many minutes, hours, however long it takes, it would actually just come to a stop. Okay. So then we would say the energy decayed, and we don't know what happened to it yet, except there's some friction around. The ideal case, it's conserved, it always swings back and forth. The most important point now, though, is that if I release it from A, it is not going to go higher than I released it from. If it went higher, then we would say there's a violation of conservation of energy. Suppose it went higher, and then on the return swing it went even higher, so I released it from A and it came back up to here. That is forbidden by the laws of nature. There's one way you can see it happen, though, is if you play a movie backwards. If you take a movie of a pendulum, it will eventually decay. If you play it backwards, the amplitudes will get larger and larger. But the reality is that it will never, in reality, be released from a point and come up higher. If you drop a ball, a very elastic ball on a hard surface, it's going to bounce, and if it's a really good one, it'll come very close to your hand. It's never going to go beyond your hand. That's the important point with conservation of energy. And in the general sense that we need to have to discuss it, I'm going to put down the law of conservation of energy, and that is, this is one you're going to remember, that energy is neither created nor destroyed. Energy is neither created nor destroyed. Okay. It's the capacity to do work. So in fact, let's continue this thought briefly. It changes form. It changes form. Okay. And the different kind of form changes we already know now. We know that potential energy can change into kinetic energy, can change back into potential energy. So that's a form change. Later this semester, we're going to see that it changes into heat. But we're not there yet. Okay, right now we're in the world of physics, purely mechanical phenomena, no heat. Okay. But this is the law of conservation of energy. If I ask you this later on an exam and you say something about turning the lights off when you leave the room, that's conserving energy, but it's not the law of conservation of energy. So the energy is neither created nor destroyed, it's changing form. If the pendulum were to be released here from rest and swing higher than we released it from, then we would have said, we would have had to conclude that some energy was created, more than we started with. And that's against the law of nature. Okay, so we're going to have more examples of this, but this is such a fundamental law. The pendulum and these concepts is the best place to start with it. When we had the asteroid collision last time, it had a lot of kinetic energy. It blasted that hole into the ground, which did work of excavation. There was undoubtedly an enormous amount of heat created. Okay. But we haven't dealt with that yet, so we weren't able to put it into our calculation. Our simple calculation was purely kinetic energy and then the work. So let's leave that there. Now my next topic is hydropower. This is actually a central part of the entire semester that we'll return to a lot. I'm going to start it off by showing some pictures, and I'm also doing an experiment here. I'm going to hold some pictures I have in front of the camera. Now I know the camera would make very, very clear images, but I'm not sure how good it's going to be on YouTube. So what you want to do is I hold this up in front of the camera. Go ahead and try to take a screenshot and print them out, okay? Print them out as a screenshot, and I have these files I can email them to you if need be, but we're trying to see how, this is the first one, by the way. I'm gonna stand here and narrate. So let's see. That would roughly be the whole thing. It's a giant water wheel, and if you can get a good screenshot of this, let me know. That's a giant water wheel. And I'll just put these notes up here. You want to have these in your notes. So, image, water wheel crane. It's actually a water wheel crane where there's water shooting down over an enormous wheel. This thing has an axle, and it's lifting some buckets there. Okay, I'm not going to try to draw it. You've got water coming in, turning a wheel, and the wheel is being used to do some work, to lift buckets. So that's why it's a water wheel crane. And if you're doing work with it, say work to lift a bucket. And it's interesting, it's an old woodcut picture image, so it's hundreds of years old. This is some old technology. But yeah, that is water wheel doing work, that is hydropower. So we're starting with a really basic example. So this is the first image. And like I said, try to get a screenshot and print it out and see how good it is. I can also send you we'll probably do both. Send you the file in the email, but we want to see how well this works. So there's our first image for the hydropower subject. And the second image is a really involved picture. So again, I'm going to show it to you. These are historical, really, I think they're important. So that was the water wheel crane. This one here is an idea that somebody had, 1673. There we go. So you'll see if we can get an image of this thing. Screen capture. Yeah, okay, so that second image is an attempt to design a perpetual motion machine. Perpetual motion machine. Now, it's a very complicated, involved, interesting sketch, and it's something that cannot work. That would violate the law of conservation of energy that we just talked about. What's basically happening there is there's a tank of water that's elevated, and water is going to shoot out and turn a paddle wheel. This is inside a room instead of outside like that first image. But the idea behind it is that not only does the water fall into the tank down below here, it's turning a paddle wheel and doing work. There's a bunch of gears and stuff involved. But a device has been built in to also lift the water via an Archimedean screw back up into the tank. So what we're trying to do is circulate the water so that it does work here, and then it gets lifted back up to the tank so that the process can continuously go on. So that is forbidden, but there's a point in history when people were trying to design these things because they understood work, they understood machines, but they did not yet understand conservation of energy. And by the way, that historical epoch has never ended because there are still people who try to make clever devices that will get more work out than is put in. So for an energy class, we have to spend enough time on this topic to really put it to rest and understand why it's impossible. Well, my pendulum is actually still up here. Asking a perpetual motion machine to give you extra work is like asking a pendulum to swing higher than you raised it, okay? It's like wanting a ball to bounce higher than you dropped it from. There are an infinite number of examples. It can never work. So these two images, we definitely want them in our notes. So first thing to do is get a screen capture and print them out and see if you can study them and understand them. And let me know. Let me know in the email because I can send you the PDF files that I made of these images, and you can print them out in high quality. But I know the camera is good enough. I'm not sure if the YouTube and the screen capture resolution is also that good. So give it a try. These perpetual motion machine and the water wheel crane, they're important for discussing putting water to work as hydropower and not following an impossible path as in the perpetual motion machine. Okay, I'm going to check how many minutes we are. Okay, fantastic. So now we can talk about hydropower. So now, after we've put to rest the idea of building a perpetual motion machine, we have to understand, how is hydropower really used? And I'm going to give the theory behind it, which is so basic we can completely understand it. And I want you guys to get some nice pictures. I usually have a major set of slides that we can look at. And not just a major set of slides, we actually can visit hydropower plants using Google Earth. You know, we can fly in there and inspect all kinds of interesting stuff. We'll see how far we get, how much of that we can do. So for the moment, I'm just going to outline it and again ask you to get good images for all of these things. So homework, hydro power images. You know, print out, show me that you printed it out, put it in your notes, and then add it to your notes. So print out, etc. So here goes the concept of the hydropower plant. The first thing is, this is a large sketch. First thing is that we have to have a lake. Okay? And typically a dam is built across a canyon or a valley or something so that a lot of water builds up behind the dam. Okay, so we have a dam and we have a lake behind the dam. Well, I've got colors here, I'll do some blue. Okay, so there's the water, lake behind the dam. Now it's important that this water line here, the top water line, be above our power plant, because this lake represents a mass of water that is elevated. In other words, it represents work. So if we put the powerhouse down here, we'll put a powerhouse here, powerhouse. Then if we can generate power, then with respect to the powerhouse, this water is elevated. And I'm even going to draw a lower lake. There's, you know, typically the big lake is up here, but there's a lower body of water down below too. And it's the height difference between those two that tells us how much energy there is. So this height difference, H, and we can now say the water in the lake represents stored work or potential energy. So the water in the lake, which is to say the water behind the dam, has potential energy and we know that stored work is the mass of water times G times H. Okay. So the next thing is that a pipe has to run down to the powerhouse. That's what sends the water down there. Okay. And this pipe here, or tunnel, is referred to as the penstock. You've got dams, you want to get pictures of a dam, you want to have the penstock. That's that pipe. And you could say, well, the water has potential energy up here when it's rushing through the pipe. Penstock, it has kinetic energy, and then it's going to spin the turbine down here, so there's a turbine inside the powerhouse. So let's write turbine and generator. Okay. And these are all things that you want to have images of. For example, a modern hydropower plant is so large that the tunnel, the penstock, could be as big around as the visible, actually bigger than this board here that is in our field of vision. Enormous. Turbine and generator, and electrical energy is generated, electrical power, and then somehow it gets transported away with power lines. We'll deal with the power lines later on in the semester. We're talking about electricity, but I'll just put that here as well, power lines. There's a whole lot going on, so we won't get it all at once. I'll underline these things in red that we want to make sure we have images of all this stuff. Okay, that's a pretty good picture. Yeah, these labeled cartoons are a major part of how we're trying to learn these things. We've been doing a lot of sketches. This is yet another one. Now, so here's the process. You've got the water in the lake. It represents potential energy. You'll notice this is the same expression for the pendulum clock and the weight in the pendulum clock. It is mgh. Now, how many joules is this? An enormous number, because it's the mass of the entire lake full of water times g times a very large h. I'll put some numbers in here later, but it's important to recognize it's the same formula. And we will later on talk about, or we'll actually mention it now, how did the water even get up in that upper lake? How did the water get in the upper lake? Well, it flowed in, or it rained in, or it snowed in, okay? So originally it was precipitation of some form that evaporated basically off the ocean. Since it evaporated off the ocean, we're talking about the water cycle, and the energy that carried the water up to the lake in the first place is solar energy. So this whole hydropower cartoon, which we're even going to expand on, is really rich. It's got pretty much it will have the entire semester's worth of knowledge on one board. Okay, so that's our hydropower situation. And now we're going to apply our concepts. How are we doing here? Okay, good. So now we're going to apply the concepts. Very good. So next, hydropower. So I get some images of this stuff. I have labeled it. I've got my H. I've got the lake, potential energy. So next, we're going to talk about the power formula. This is a great one. It's not even new. We know that power is work over time. Here, we have power is mgh divided by T. So the work is just the potential energy of the water above the lake. And T is, when it was the grandfather clock, T was just a week in seconds how long it took to run down. So we're using the same formula. We're going to do the following. Right, or P equals M divided by T. We're just going to put parentheses around the M divided by T times G times H. So it is the formula for the grandfather clock, with a slightly different interpretation. by factoring out or putting parentheses around m divided by t, I'm drawing attention to this thing. Its units are kilograms per second. Okay. So I'm going to write that over here. Continuing over here. The expression m divided by t is the flow rate. It's the flow rate. Its units are kilograms per second. So kilograms per second of water flowing through the penstock. So that's the flow rate, m divided by t. So you take that flow rate and multiply it times G times H, you get the power. But remember, the power was watts. Power units are watts. Okay. So this is the hydropower formula. The wattage, the power output of a power plant can be controlled. G and H are basically fixed. Sure, the lake can run down a bit, but in our power plants that we're going to talk about mostly, the penstock is really long. It's a long pipe that goes way down a mountainside. So the powerhouse is far away from the actual dam. Okay. So we're going to ignore the fact that the lake could run down in the dry season, and we'll just take the top of the lake down to the lower lake there, and that's the H. So that's a fixed quantity. G is gravity, so that's also fixed. This m over t can be controlled, so you can imagine dialing open a giant spigot, and the more flow you have coming through here, and like I said, these tunnels are as big as this room almost. They're enormous sometimes. We'll get some screenshots of that, by the way, later on. So yeah, you control the flow rate to control the power output. And I'm just going to give an example of that, just to give an idea. So this is a small example. Well, small is relative. Let H be 100 meters. Just over the length of the football field, that's the height, okay? We're going to just take G as 10 meters per second squared. We can do that. It's an approximation. And the flow rate, m divided by t, we're going to take that to be 1,000 kilograms per second. Now, 1,000 kilograms of water is the water that fits into a 1 cubic meter. So, okay, you've got a box. It's roughly the desk here width. So you got a box like that. This is my book here, like the tabletop, up a meter, you're looking at a cubic meter of water per second. And we'll plug those numbers into the power formula and see what we get. Notice I chose easy numbers, so now power is equal to 1,000 kilograms per second. I'm going to go ahead and put that note there while I'm thinking about it. This is 1 cubic meter of water, just so you can visualize it. So we've got 1,000, and then we've got G is 10 meters per second squared. We've got H is 100 meters. Yeah, so what do we get here? 10 to the 3, 4, 5, 6. We get 1,000,000. 10 to the 6 equals 10 to the 6 watts. That's an interesting number. It's also called a megawatt. Equals 1 megawatt. Okay? 1,000,000 watts. Okay, that's more than you use in your house. A large-scale hydropower plant can easily generate 1,000 megawatts. Okay, 1,000 megawatts for a large-scale hydropower plant. And that's what runs our whole, that's an aspect of running a big civilization, large city full industry and what have you of energy use. But it would be the same formula if it were 1,000 megawatts. It would just be a much larger apparatus. So these examples are ones that I want you to master, and we will right now just put it all into context. And notice again that this is our grandfather clock, so we know this formula. We just reinterpreted m over t as a flow rate, and now we're talking about hydropower plants. And megawatts, you could say, are the unit of energy for large-scale use. You need 1,000 of them for civilization or more. Okay, I think this is a good place to stop. Let me just reiterate the homework. We're looking for images, and we also have the images of the water wheel crane and the perpetual motion machine. So get stuff printed out, and I'll give more recommendations next time as to how we're going to pursue this. Yeah, good. See you guys next time.